Have you ever wondered how calculus helps to improve the safety of vehicles? How credit card companies use calculus for payments? How about how the space technology makes use of calculus concepts in many ways? Did you know that because of that ability to model and control systems, it gives us extraordinary power over the material world? Oh wait, that looks pretty. What is that?
It's a polar curve. Did you know that it can be used to describe directional microphone pickup patterns? Polar coordinates is also used in calculations involving aircraft navigation, gravitational fields, and audio-radio antennae.
Thanks to that, our physicists and engineers are able to innovate better machines and better understanding on electricity and magnetism. Can we also use calculus for cyclones?
Of course! Cyclones are highly calamitous weather phenomena initiating harm to the life and physical organization in tropical seafaring countries. It is an enormous-scale air mass that turns around the solid focal point of low climatic weight caused due to low atmospheric pressure over oceans, resulting in rainfall in the coastal regions. And for your information, the double integration technique has a good potential for calculating the average rainfall during the supercyclone.
Now, you can come and join us as we explore more calculus.
What is a polar curve? Polar curves are graphs of equations with polar coordinates as their basis. The polar curve, like ordinary equations and curves, is made up of all polar coordinates that satisfy the specified equation. The graph of a polar equation defined by r and theta is called a polar curve. To plot the polar curve, we utilize polar grids or polar planes, and this graph is modified by all sets of r and theta that meet the polar equation r equals f theta. The equation of a curve expressed in polar coordinates is known as a polar equation and is usually written with r as a function of theta. What are the applications of polar curves? Its applications are for robotics, aviation, and Archimedean spiral. The first one is that the polar coordinate system, or a slightly modified variation of it, is used by several robots capable of movement for navigation. Because the center of the coordinate system is always located at the robot's current location, this is particularly convenient for artificial intelligence. The second one, aircraft navigate using a slightly modified version of the polar coordinate system in the air. The 0-degree ray is vertical in this coordinate system, and the angles proceed clockwise rather than counterclockwise. And lastly, the Archimedean spiral has a wide range of practical uses. Scroll compressors compress liquids and gases by combining two interleaved Archimedean spirals of the same dimension. There are a lot of things in this world that are made with the help of calculus. And to know more about polar curves, let us explore them, especially the graphs on our next video.
As we now have an idea or a little background about polar curves and its application on real life, let us now dig deeper into its graph and how we should sketch or illustrate them. So if we already know how to plot a point on a polar coordinate system, sketching the graph will be a lot more easier. But take note that the characteristic of the graph or the curve depend on its polar equation. So we can sketch the graph by making a table of polar coordinates and connecting all of their points. However, for easier plotting of curve, we will use Desmos and observe its pattern. Okay, so for our example, we will have r equals 1 plus cosine theta. So this is the illustration of our equation r equals 1 plus cosine theta. Notice that this illustration, or this equation makes a graph that looks like a heart. So What will happen if we will change the value of a? Take note that our general equation is r equals a plus minus cosine or sine theta. So we will change the value of a and let us observe what will happen to the graph. So we will change the value of a into 2. Notice that when we change the value of a, the graph is now almost a circle. Earlier, we have a curve that looks like a heart. So what will happen if we will change again the value of a into greater than 2? And then again, and then again. Therefore, we have concluded that if we change the value of a without changing the value of b, especially if a is greater than 2, the graph will become circle. Now, what if this time we will change the value of b? So we will change back the value of a into 1. Then we will just focus on the value of b. So what will happen if we will change the value of b? We will try to change the value of b into 2. Okay, so we can see here that we have an interloop curve. If we change the value of b that is greater than 1, we can have an interloop curve. We will call this loop here as an inner curve, and then we will call this one as the outer curve, so that we'll have an easy interpretation of the curve. Okay, so now we have observed the changes of the curve or the pattern for the value of a and the value of b. This time, we will change cosine into sine. So what will happen if we will change our equation into sine from cosine? So we can see that the graph or the curve is congruent compared to cosine earlier. So the only difference between them is their position. So if we have cosine in our equation, our graph is horizontal. But if we have sine in our equation, our graph will become vertical. But what about if we change our operation from addition to subtraction? So we now have a 1 minus 2 sine theta. So the only difference is that it flips vertically. But if we have cosine here, of course, it will just flip horizontally. Therefore, if we have a subtraction operation, the graph will be on the negative side of the polar coordinate. If we have addition operation, of course, our graph will be on the positive part of the polar coordinate. So now, how can we know the height or the length of our inner curve and outer curve? How can we know their height horizontally or vertically? So we will just simply add the value of a and b. So here for our example, 1 plus 2 is equal to 3. So here, our outer curve is on the point 3 from origin in our x-axis. And then for the height or the length of our inner curve, we will just subtract 1 from 2 or subtract a from b. So 2 minus 1 is equal to 1. So we have here the length of our inner curve, 1 unit. So the graphs that we are using since earlier is what we called limacon, and the other one is cardioid. So cardioid can be created if the values of a and b are equal. So to satisfy our observations, we can have the sample equation 3 plus 6 cosine theta. So to satisfy our observation, let us have this example 3 plus 6 cosine. Plus 6 cosine. So again, as we have cosine in our equation, as what we have observed earlier, the graph is horizontal. And then, the length of our outer curve, we will just add 3 plus 6. So we have 9 units for our outer curve. So we satisfy our observation earlier that we just add the value of a plus b for the length of our outer curve, and for the length of our inner curve, we will just subtract 6 and 3. So 6 minus 3 is equal to 3. So here we can see that the length of our inner curve is 3 units. Okay, so for our next example, we will have 3 plus 3 sine theta. So our graph is vertical. It is because of our equation sine. So notice that we don't have an interloop. Why is it that we don't have an interloop? It is because of the value of a and b. So the value of a and b here in our equation is both 3. Therefore, if we have an equal value of a and b, we will have a graph that is called cardioid. And also, our observation earlier still can satisfy this graph for our inner loop or inner curve. So for our inner curve, we have b minus a. So 3 minus 3 is 0. Therefore, we don't have an interloop or we don't have an inner curve because of the difference of b and a, which is 0. And then for the height or the length of our outer curve, we have 3 plus 3, which is 6. So to summarize, here are our references that we have taken note earlier. So if the value of a is less than b, we can have or we can create a graph that is called limacon.
If the value of a is greater than b, we can have a graph of a circle.
If the value of a is equal to b, we can have a graph of cardioid. And if we have cosine on our equation, our graph will be horizontal. And if we have sine, of course, we will have vertical graph. So if we have an addition operation, our graph will be on the positive side of the polar coordinate. And if we have a subtraction, our graph will be on the negative side of the polar coordinates.
Earlier, we have explored lemacon and cardioid. They have an equation r equals a positive negative b sine theta, or r equals a positive negative b cosine theta, where a and b must be greater than 0. Now, we will observe another curve called rose. It has an equation r equals a sine n theta, or r equals a cosine n theta. Note that a should not be 0 and n is an integer greater than 1 to achieve this curve. Just like earlier, we will have this basis to simply explain the pattern of curves a, n, cosine, and sine. So, as we can see here, we have the sample equation. As the value of a changes, the range or length of the petal also changes according to the value we have substituted to a. Now, let us try to change the value of n. For 3, we have 3 petals also. If we have 4, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 petals. Let's just continue to change the value of n. We have observed that if the value of n is an even integer, the number of petals double. While for the odd number of n, we get the exact number of petals. Let us explore this sample equation. So again, a is 4. So we have the length of petals on 4 units. Then we have 7 as the value of n. 7 is an odd integer. Therefore, there are also 7 petals on the graph. What will happen if we change sine to cosine? Notice that in this equation, where we have sine, there is one petal that aligns the y-axis. Therefore, the graph is vertical. While for cosine, one petal aligns x-axis, which means the graph is horizontal. So sine is vertical and cosine is horizontal. Again, a for the length of the petal we have, n for the number of petals depending if it's odd or even, and lastly, cosine for horizontal graph and sine for vertical graph.
Now, we are done exploring the graph of the curve and how its pattern works. So this time, we will now show you how to solve for an area of an enclosed region using the tree-leaved rose as an example.
Okay, so let us now recall that the area of the sector of a circle is solved by the equation or formula A equals 1/2 r squared theta. So if we want to find the area of a region that is defined by a central angle and a polar curve, we can use this formula. For polar curves, we take infinite small sections of the region area and take Riemann sum. So deriving the formula A equals 1/2 r squared theta, we can have the formula for our area for enclosed region A equals the integral of 1/2 f theta quantity squared d theta from A to B, which can also be written as A equals the integral of 1/2 r squared d theta from A to B, as we know that r is also equal to f theta in our polar equation. So let us now try to solve our equation earlier, 2 cosine 3 theta. Take note that our A and B can be determined by the central angle of our illustration. So how do we get the angle? So we have here the illustration 2 cosine 3 theta, which has a curve or rose illustration that has one petal aligned on the x-axis, and on the other one is on the second quadrant, and the last one is on the third quadrant. So we will use this first petal to determine our A and B from the angle bounded by this one petal. We all know that this part of the polar coordinate is from 0 to 90 degrees. And then we have the value of n, which is 3, so we will just divide 90 over 3. So 90 divided by 3 is equal to 30 degrees, which is also equal to pi over 6. So our A is negative pi over 6 and our B is pi over 6. Now we have our values for A and B and also for R. We will now substitute our values into the formula. A equals the integral of 1/2 2 cosine 3 theta quantity squared d theta from negative pi over 6 to pi over 6. Now we will just put the constant 1/2 on the outside of the integral. So 1/2 the integral of 2 cosine 3 theta quantity squared d theta from negative pi over 6 to pi over 6. Now 1/2 the integral of 2 squared, which is 4 cosine squared 3 theta. So we will enclose this 3 theta so that we will not be mistaken to square this value. Okay, again, so we will just put the constant, which is 4, outside the integral. So 4 times 1/2 is equal to 2. So we will just put 2 here, and then integral of cosine squared 3 theta d theta. Recalling the power reduction identity, cosine squared is also equal to 1/2 times 1 plus cosine 2 theta. Cosine squared 3 theta is also equal to 1/2 times 1 plus cosine 6 theta. Then putting it on our formula, we will have A equals 2 integral of 1/2 times 1 plus cosine 6 theta d theta from negative pi over 6 to pi over 6. So again, we will just put the constant 1/2 outside the integral. So we now have 2 times 1/2 is equal to 1. So we will just disregard the 1 and write integral of 1 plus cosine 6 theta d theta from negative pi over 6 to pi over 6. Now, the antiderivative of constant 1 is theta plus the antiderivative of cosine 6 theta, which is sine 6 theta over 6, ranges from negative pi over 6 to pi over 6. Now we will solve for its definite integral. So we will just substitute first the b from all the theta. So pi over 6 plus sine 6 times pi over 6 over 6 minus negative pi over 6 plus sine 6 times negative pi over 6 over 6. So pi over 6 plus sine pi, as we have cancelled 6 here, over 6 minus negative pi over 6 plus negative sine pi over 6, as we also have cancelled 6 from sine 6 and negative pi over 6. Next, pi over 6 plus 0, as sine pi over 6 is equal to 0, then minus negative pi over 6 plus 0 also, as the value of sine pi over 6 is 0. So we have pi over 6 plus pi over 6, as we have here minus and negative sign, so it will become positive. So pi over 6 plus pi over 6 is equal to 2 pi over 6 or pi over 3. So the area of one petal is pi over 3. So in total, we have 3 petals, so we will just multiply it by 3. Pi over 3 times 3 is equal to pi. We have a total of pi for our equation 2 cosine 3 theta.
Good day, everyone. This time, I and Jeanica Ybañez will going to discuss the part 2 of the major task for Calculus 3. I am going to start discussing about the definition of double integrals and what are its application. So, double integrals are a way to integrate over a two-dimensional area. It is used to calculate the area of a region, the volume under a surface, and the average value of a function of two variables over a rectangular region. The definite integral can be extended to functions of more than one variable. Consider, for example, a function of two variables z is equal to f of xy. The double integral of functions f of xy is denoted by the double integral of f of xy dA over r, where r is the region of integration in the xy plane. So, there are different applications for the double integrals. First, we have finding area using a double integral. We have already seen how double integrals can be used to find the volume of a solid bounded above by a function f of xy is greater than or equal to 0 over a region of r, provided that f of xy is greater than or equal to 0 for all xy in R. Next, volume of an elliptic paraboloid. Then, calculating average storm rainfall. Similarly, we can define the average value of a function of two variables over a region R. The main difference is that we divide by an area instead of the width of an interval. Lastly, solving average value of function. In this example, we find the average value of a function over a rectangular region. This is a good example of obtaining useful information for an integration by making individual measurements over a grid instead of trying to find an algebraic expression for a function. Now, I am going to give the floor to my partner Jeanica Ybañez to give an example about double integral and further discuss the solution.
Now that we have already known the definition of double integral and its application, We can now have some problem solving that involves double integral.
If one variable gives you an area which is a is equal to the function of x dx bounded from a to b, then two variables gives you the volume. So in here, we need to find the volume under a surface bound by a region. We are not finding h or length times width anymore. Here we are finding h multiplied by an area or surface area. So on xy plane, we are going to find a rectangular region and we're gonna cut it into equal size rectangles. So here is the region that we get from the 3-dimension figure. So in this rectangular region, so the number of partition of x from x-axis is called m, and the number of partitions and y-axis is called n. In this region, we have 1, 2, 3, m. So m is equal to 3. And the n is equal to 2. Next step is we need to pick a point for every sub-rectangle, and these are the x sub I j dot and y sub I j dot. So these are the arbitrary point or the x. We need to find this arbitrary point by pointing it from the x coordinate of every rectangle. So here are the points for every rectangle. So here is the point for rectangle 1, 1, 1, 2, 1, 3 if ever nga may dyan kita. Next is 2, 2, 2, 1, 3, 1, 3, 2. So next step is we need to plug it in to find the height of this region. We all know that functions always gives height. So we have this f sub x sub I j dot and y sub I j dot. So to find the volume, we need to have a surface area times the height of each function. So we have this volume is equal to surface area times the height. So if x is an element on the interval AB and y is an element on the interval CD, we are now cutting x into m subintervals. So we have this b minus a over n is equal to delta x, and this delta x is the width of our rectangles along the x-axis, of every rectangles along the x-axis. And for the next one is d minus c over n is equal to delta y, which is the height of every rectangle in the y-axis. So given this na found natin, we can now have the area of each rectangle, which is delta x, the width, and delta y, which is the height. And they are all identical. So we can now find the volume for each rectangular prisms, since we have the area, the delta x times the delta y, of each rectangle at arbitrary point f of x sub I sub j dot and y sub I sub j dot. So we have this one. V is equal to f of x sub I j dot and y sub I j dot times delta x times delta y. So this one is the height, this one, the delta x, is the width, and the delta y is our length. So we can now have the volume of each rectangle, then the entire volume of the area under the surface, which is the summation of the function x sub I sub j dot, y sub I sub j dot times delta x, delta y. If you are adding across two different dimensions, we need two different sums. So we have this one. V is equal to the summation of the function x sub I sub j dot y sub I sub j dot delta x delta y from I equal to 1 and j equal to 1. So this volume is just an approximation. Why? Because we have finite number of rectangles. So to get an exact volume, we need the number of the rectangles to go to the infinity. So we need to have this v is equal to the summation of the function x sub I sub j dot y sub I sub j dot delta x delta y as I equal from 1, j from 1, as m and n approaches infinity. We all know that the limit of the sum gives us the integral, and the limit of two sums gives us two integrals. So we will now have this equation. Double integral over region, and where this one f of x of y is a function at arbitrary point with two variables, and this one, now every time we have delta x and delta y going to 0, we will have dx dy. So for any function of two variables, the volume under the surface and over a specific region is given by the double integral over the region f of x, y, dA. That is what the double integral means. Now, it is giving us the volume under a surface and over a certain region. So we have this equation to find the volume over a region and under a surface area. So double integral over a region of f of x of y, x, y, dA, where this dA stands for area of every rectangle. So area of every rectangle, it can be in this two way. So area of or delta A is equal to delta x times delta y, and it can also be delta A, or the area can be equal to delta y times delta x. It is equal because it is a commutative property. So dA is equal to, can also be equal to dx times dy. So but if delta A is also equal to delta y and delta x, it can be also, dA can also be dy times dx. So in this equation, R should be defined. So this means that for rectangular regions such that x is bound by a constant. So it means that if I have a rectangular region on xy plane, then it has to be bounded by constants. This is what it looks like. This is our region. So because of dA relationship, that means that there is actually two ways to set up any double integrals. So the first one, we have this first. We drew two integrals, f of x, y. What should we do next? Whatever comes first, it should be connected to the variable bounds at the region. So if we put dx first, the inner first integral must be the value of x. Same as true if we put first the dy, the inner first integral must also be the variable of y. We must match up the correct numbers with the correct variables. So for your information, these two equations are equal or the same. Both are right, and this is the Ybañez theorem for rectangular regions. But we should choose the one that is easiest, because sometimes the way we set this up can make our problem much easier or much complicated. We will now have the example. Evaluate the double integral over region or R f of x y dA, where f of x y is equal to 2xy, bounded by a region such that x is greater than or equal to 0 and less than 7/4, and y is greater than or equal to 0 and less than or equal to the square root of 2 minus x, by finding the volume of the corresponding solid. So here the region are all the ordered pairs on xy plane. So that satisfies the following conditions. So if we draw the region, it will look like this. This is y equal to 0. This is y is equal to the square root of 2 minus x. This is x equal to 0. And x is equal to 7/4. So when you set up a double integral, you can do whatever you want. Now you can do the dx first here, or you can do the dy first and then the dx, or the second. So if you go with dx first, that means you are going to integrate with x direction first and then y. If you're going to integrate first dy, you are going with the y direction first and then the x direction. So to help you decide on which direction to go first, going to the direction along whatever axis is always between two functions and not switching between two different functions. So in our case, if we go with the x-axis first, take a look at this pattern. Notice that it is going between the two functions. The function x equal to 0 and then the x equal to 7/4. But suddenly it changed upon reaching here. So there is a change of function, nag-change ng function. But if we go along with the y-axis first, it does not change or is going between the same function. So we will gonna set up our double integrals this way. So we need to go first to integrate first in y-axis direction and then the x direction. Another tip is whatever is on the outside the integral, it must be always constant. Why? For us to be easier to plug in at the end of integration process, not to get the result of actual numbers. So we will now have this double integrals. So this is the equation of 2xy dy. We will go first with the y. And for the first inner integral, we need to put with what is the value of y. It is 0, from 0 to the square root of 2 minus x. And then next one, dx, and the value of dx outside is 0 and 7/4. So notice that this dy, we put dy first, and this variable must match up to the first integral. And now we will proceed to the antiderivative with respect to y. What is the antiderivative of this with respect to y? So this is 2xy. We need to add 1 sa y. We need to add 1 sa exponent and y, and then over 2. And we will come up with this xy squared. And then next step is let us now evaluate with y variable. So what is the y variable? 0 to the square root of 2 minus x dx. And then next step, x 2 minus x, the minus, we plug in the value of y first. The first thing that we need to plug in is the upper part, which is the square root of 2 minus x. So plugging it in, the radical sign will be cancelled. Minus, plug in 0 to the y, and it will result to 0. So we have this equation. And then next step, it's easy now, because we need to find the integral of 2x minus x squared dx from 0 to 7/4. So what is the result? It will come to x squared minus x cubed over 3 from 0 to 7/4. So the last step is we will plug in the value of x. So we have this 49 over 16 minus 343 over 192, and it is equal to 345 over 192. This is now the answer. So 345 over 192 is the volume of this solid. Another tip is we need to get our regions correct, because if you get it right and you set up right, things will go smoothly. Double integrals are the volume under a surface over a defined region, but how you set it up doesn't matter. It can be you can integrate dx first or dy first. It doesn't matter, huh? But you got to set the x bound with dx and y with dy.
We can use the double Riemann sum to approximate the volume of a solid bounded above by a function of two variables over a rectangular region. By taking the limit, this becomes a double integral representing the volume of the solid.
Properties of double integral are useful to simplify computation and find bounds under values.
We can use Ybañez theorem to write and evaluate a double integral as an iterated integral.
Double integrals are used to calculate the area of a region, the volume under a surface, and the average value of a function of two variables over a rectangular region.
That is all for our presentation all about the double integrals.
Thank you, and I hope you learned something out of this video.